Assalamualaikum warahmatullahi wabarakatuh. Hello everybody. Nice to meet you here. This time we would like to discuss the kinetic theory of gas second part on Maxwell-Boltzmann distribution. By understanding and learning Maxwell-Boltzmann distribution, we can calculate root mean square speed, average speed, and most probable speed. Actually, in the previous meeting, we also already calculate the speed of root mean square, average, and most probable. The difference is, last time, we learned and derived it from the gas pressure and momentum, but today we would like to calculate it from Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution gave the distribution of molecules in terms of speed and velocity and also energy. So by understanding of the distribution, then we know the fraction of the molecule in certain distance that have certain velocity. As you know, and we already learned in the previous meeting, that gas is always move in random movement. And the movement is on x direction, y direction, z direction, meaning in three-dimensional direction. If we write the direction in x direction and we represent it by Vx, V velocity and x is the direction. As you see in the presentation, dn per n, that is the fraction of the molecule, and A over there is the constant ratio. And so the fraction of the molecule is proportional to E power by minus half times m, then velocity on x direction divided by kt. K is the Boltzmann constant, m is mass, v is velocity, T is temperature. You can see over here, when the temperature is higher, then the fraction of the molecule will be greater. So next, we would like to calculate the distribution. We would like to count the A constant, the ratio constant. Let me go to the whiteboard. I will show you how to calculate it. So the fraction of the molecule that we represented by dn per n is proportional to E per minus half m, mass of the molecule, V is the speed of the molecule, and x is the direction, square, divided by K is the constant of Boltzmann, and T, temperature, dVx over here, and time A, the ratio constant. Ratio constant. When we integrate that number, that equation, with the Vx from minus infinity to plus infinity, and we should get 1 because this maximum value. Okay. So then we can count actually what is the value of a constant, ratio constant over here. It is not quite hard actually. So A is equal to 1 divided by, so this is from minus infinity to plus infinity. This, okay, E minus mvx kt dvx. It is a bit tricky actually because we have to calculate this one first. We remember from the mathematics solution over there, have a look in the presentation, that so here can be written as easy like this. Let's have a look over here. So that one, let's say written by something like this. Again, here is E mvx squared per kt dvx. Okay, and we can write it by here. Okay, E mean A V squared dv. And we remember the mathematics solution over there. When we have that, when we have the equation like this, and this n, okay, E minus AV squared dv. Have a look A over here. We have V over here. So A is equal to this, meaning that A is equal to minus a half m per kt. Let's go back to this equation. When we have n is equal to 0, E dv, then here we have the solution is the root of p per a. When n, have a look over here, sorry. When n is equal to 1, then we have v e mean av dv, and this equal to 0. Now let's have a look our first our equation. Our equation is this, meaning that we have n, v here is powered by 0. So meaning that we have is equal to this. So here is p per a, and a is this. Sorry, this should be root of that. Okay, so we know that exactly from that equation already shown in the PowerPoint presentation, that A is equal to that from that one, and divide it over here. A is equal to, you can see in the presentation. I don't think that someone do not understand how to find the ratio constant value A. And I'm sure that you can follow us, you can follow me to calculate the constant ratio values. Let's go back to the presentation. So from the equation over there, then we can have it that our equation is like this. Have a look here in our whiteboard. Have a look this. That the fraction of the molecule is equal to, here is m per 2p k t a half. Okay, E something like that. Okay, and here is x because in x direction. What happened? Because I already mentioned this is only for one dimensional direction, but we have actually three-dimensional direction, that x, y, and z. So we have to remember this, because this only one, okay, one direction. So we can now write our equation by, this must be 3/2. Why? Because the direction is in 3 dimensions. And time E, okay, half m, and V here is V, not Vx, not Vy, but V, square per kt dV. In exactly, we have dV here, dVx, dVy, and dVz. Also this, also Vx, Vz, and Vy. So our equation now is becoming this, because in 3-dimensional direction, as you can see also, it is actually the same as given, as written, as shown on the presentation. But as you know that here is P, this one is P. Remember that. Okay. So now you have to remember, if we reshape box, so the container in box